Welcome back, everybody, from morning tea. I hope you've had a great snack, time to catch up with people, and have some refreshment. Apologies, this is my first time emceeing, and it all happened within the last 10 minutes. So, this is really agile software development on the fly. So, apologies if I put my foot in my mouth. So, this morning I'd like to introduce Brian, who's coming to us from sunny Ontario in Canada. Currently minus 30 outside for all of those of you in Sydney that are suffering from 30 plus. We're from the west coast of Australia and it's even hotter. Just think of them in Canada, minus 30. I think our sunny Australian coasts are a little warmer than Canada at this time. So Brian is joining us so we can learn about how Hootsuite used load testing to evaluate the performance of Prometheus and Grafana based metric platforms, developing a framework based on open source tooling Locust that can be used to quickly evaluate the performance, impact of configuration and component changes prior to deployment. Now, Brian's talk is pre-recorded in case we have any technical glitches across the Pacific, but Brian will be joining us again for a Q&A at the end. So Brian will be live. That is him there live at the moment, nodding along. It's not just a noddy. And those plants in the background are real. They're not even a virtual background. So we really, really have him here. Thanks. Enjoy the session. There'll be a few seconds pause as we switch over to the recording. See you soon.
Welcome to the inaugural voyage of benchmarking Prometheus metrics platforms. My name is Brian Groux, and I'm a senior software developer at Hootsuite, and I mainly focus on observability. So some background, we implemented a Prometheus, Thanos, Grafana stack to support multi-window, multi-burn rate alerting for most of our product software, but also for some of our infrastructure as well. After the initial implementation, we received reports from developers that their dashboards were loading slowly. And while we could load these dashboards and see that some were slow, others were performing fine. So we really didn't have an idea as to the extent of the problem. We really had no empirical data to prove that things were actually running slow or how many things were running slow. So we set out and we thought to ourselves, how can we verify and also tune the performance of the current metrics platform we have, but how could we also possibly benchmark other Prometheus-based solutions? And so our answer was basically we want to performance test our infrastructure. So you may be asking yourself, why performance test your infrastructure? It's our belief that infrastructure critical to assisting product development should be just about as critical as the product itself. It also helps you understand baseline performance. It helps you validate changes against existing baselines before changes actually get integrated. It helps you watch for regressions in the system itself, and also to allow you to be proactive. So if you're running this in an automated fashion or manually on a cadence, you can catch problems before your users actually start complaining. So first we set out to figure out how to model these tests correctly. So generally speaking, we want to understand end user performance, and we want to understand end user performance from the perspective of the client that our users are accessing to query the metrics platform. So more specifically, we were looking to assess the performance of our Prometheus or Thanos platform, which was accessed primarily through Grafana dashboards. So to this end, we thought we would actually model the performance tests themselves after actual Grafana dashboard loads. So the first question became, how is Grafana loading dashboards? And Chrome developer tools to the rescue here. We basically loaded a dashboard and watched and saw what was happening. So unsurprisingly, Grafana is making HTTP requests to its own backend, and then it would proxy these requests over to the Prometheus or Thanos backend. And their request path was basically the same as what you would throw on a Prometheus API request. So it's easy to copy pasta. The next question became, what are these requests actually doing? And again, we're in Chrome developer tools. So first we could see that template variable queries were being run, and that there's actually dependency resolution between the variables. So if you had multiple template variables, Grafana would actually figure out the order in which to make those requests and then kind of request them top down. And next, Grafana was loading panel queries, and it would start by requesting all visible panels concurrently, and then as you scrolled, it would request the other panel queries as those panels actually became visible. So the question became, do we have to replicate this complex behavior precisely? And my thought was, no, you just need to determine the best way to approximate the client's behavior in a way that your performance tests still make sense. And for this use case, we decided to approximate the behavior I just talked about by first serially loading all the variable queries and then loading all the panel queries in parallel. And this would kind of provide us a worst case scenario for loading a dashboard, in that all panels were actually loading at the same time or visible at the same time. So next, the question was, what specific requests should we actually be making? And as I said prior, we wanted to simulate the user behavior. So we came to the conclusion that no one knows how to break our stuff better than our own users or our developers. So we should actually model these tests based on existing dashboards. And the alternative would have been just to generate some synthetic load, perhaps requests that we know are problematic, but maybe not as true to form as behaving like a user. So the last question was, what is Grafana actually sending in these requests? And surprise, surprise, it's PromQL with the variables evaluated. And it's like, wait, what? More variables? Yes. So there are template variables in here that we had already kind of talked about, and these are either static or generated dynamically from like a PromQL query. And there's also built-in variables, things like range and underscore. So how did we decide to handle variable evaluation? Well, we decided for the built-in variables that we just set some same defaults to things like interval for 5 minutes, and range was obviously going to be calculated based off the start and end dates. We decided for the query-based template variables that we would actually still make those requests to Prometheus or Thanos, and that this would help better mimic the dashboard load. However, we also decided that we would use the template variable default values in the actual panel queries themselves, as these were the default queries with those default values for those variables that were actually run when the dashboard came up. And beside, we didn't have a great way to say which value we should actually be substituting anyway other than the default. So to kind of recap our modeling section, we decided to make multiple HTTP requests to our metrics backend to replicate the load. We're going to serially request all template variables first, then move on to concurrently request all the panel queries. We were going to model the request order and content based on existing dashboards that we already had, and we were going to set sane built-in and template variable default values, but we're still going to make those variable requests, the variable query requests to the backend. So before we actually set out to do this, we wanted to come up with a testing methodology and also some boundaries for our tests. So in the center here, you see a standard software development lifecycle that everyone should be familiar with. And we thought we could apply this to our performance testing as well, in that we could come up with a hypothesis, this thing is slow because of this or that. And then we could come up with a design of how to prove or disprove that hypothesis. Maybe we can throw more resources at it, or maybe we can tweak configuration in some manner. Then we'd actually make those changes once we figured out what to do. Then we would run a standardized test suite to verify and benchmark those changes, and then the results from the test suite could feed back into a subsequent hypothesis. So just to kind of recap some of the tenets of this methodology is that it's systematic and that it provides us a framework to develop and prove out these hypotheses. And it's consistent in that the same tests are run on every iteration, which actually allows every run to be compared to previous runs. And it's data driven. Test feedback, the test data actually feeds back into the decision-making process. And in addition to the test data itself, external data can also be integrated into the analysis phase. So if you have metrics from somewhere else, or logs or traces or whatever else you may have, you can use that to influence your analysis phase as well. And lastly, the methodology is iterative. It results in this kind of tight loop where changes can be evaluated quickly and hypothesis can kind of evolve with each iteration, which hopefully leads to an increase in velocity. So just a quick note about data validity here. A data-driven process like this one is really only as good as its input data. So we started thinking about what happens if during one of these tests, if a service goes offline or if it temporarily slows down, let's say because someone else is using the service in the testing environment. So we actually had decided to smooth out the data for the tests by running the tests multiple times and then using an aggregate of the result instead of just running the test once and using that in case that test run happened to be botched or influenced by external factors. So lastly, we needed to decide on some boundaries for our tests. We found our longest common use case for a dashboard was basically about 30 days. And we noticed Grafana didn't have many concurrent users, so we decided to cap the maximum number of virtual users we simulate to about 10. Then we had decided that we would run each kind of test suite for user loads of 1, 5, and 10, and each one of those for 1 day, 3 days, 7 days, and 30-day windows. So each one of these combinations would actually be ran 10 times to smooth out the data and just kind of ignore any external factors that may be influencing the test and kind of smooth that out. So now we had a methodology. We wanted to come up with a testing platform and a design for our tests. So a little note on technology selection. We needed a tool for load testing that could make HTTP requests, and there's lots out there. We also needed to simulate multiple users, so many load testing tools kind of fall into this into those requirements. And Locust had actually been used in the past at Hootsuite for load testing different things, and we'd actually used it for load testing individual Prometheus servers. And time had also been invested in the tool to make sure it ran on Kubernetes for us and some other tweaks here and there. So given all this, we decided to move forward with Locust. So to bring forward some of our requirements from the modeling and methodology sections and how these implements our tool, we needed to serially make HTTP requests for these template variables, which is met by the default Locust HTTP client. And we needed to concurrently request all the panel queries, which is something Locust does not handle. We also needed to execute requests for multiple dashboards multiple times and provide an aggregate of the results, which isn't really met by Locust, but it's something we'll address in our test design in a minute. And we also needed to expose data to feed back into the analysis phase of our testing loop, which was met by Locust as it has this web UI that allows you to export CSVs. And while it's not terribly automated, it worked for us where we could just take that data and dump it into another sink like Google Sheets, for instance, is what we used for doing most of our comparisons. So the first step was adding concurrency into Locust, and Locust itself is Python-based, both the tool and the authoring. And as people who are familiar with Python know, concurrency isn't necessarily known to be one of its strong suits. But we did find this AIO, async IO HTTP client to be the kind of recommended solution for doing this thing. So we proceeded to implement a Locust client based on this package. It did take some time to kind of figure out the exception and error handling with async IO. So we weren't doing things like exploding the event loop or swallowing exceptions in the event loop and not passing those back to Locust so they could actually be reported to the error statistics that are displayed on these dashboards as well. Also, Locust can run n virtual users per node, essentially, and we never really figured out how to get this working with async IO, despite trying things like creating an event loop per Python process or per async IO client. So the client overview, I mean, the idea here was to expose the method to make a list of requests concurrently, but we thought it would also make sense to encapsulate a base HTTP client so the consumers can request both serially and concurrently with the same client. It also, as I said prior, like it creates this new async IO event loop per client instance, and we're still not sure this was the right approach as we never quite got it working. The async request mechanism itself, it passes back a list of these custom result objects. So if an exception does actually occur during the request, they are caught and they're passed back inside this result object, which allows our handling code on the other side of the event loop to tie that back into Locust's error reporting. A little overview of the test layout. So as you can see here at the top, we have a encapsulating class, Locust user tasks, and inside that there is two of these dashboard 1 and dashboard 2 tasks. Both are a sequential task set, which is a Locust construct from the API. And you'll notice here that the embedded classes, dashboard 1 and dashboard 2, they would declare this kind of tasks variable, which is something that's part of Locust API, and this will define the sequence of the tasks that are executed. And in the case of the dashboards themselves, these task variables are set to methods, right? So they load the variables, they load the panels, and then they stop the dashboard load. And dashboard 2 would do the same thing. It would load the variables, load the panels, and stop the dashboard load. And then you can see for the Locust user tasks outer class that there's also a task variable declared, and that's basically deferring to the inner classes. So it wants to load dashboard 1 and dashboard 2, and then to repeat this for those 10 times, you just kind of repeat that for as many times as you want to run dashboard 1, dashboard 2, dashboard 1, dashboard 2, etc. And then at the end, you have to say stop test again. And stop test and stop dash, they're not shown here, but they're really just methods. They call an interrupt on the Locust test itself to stop things from executing over and over. So now we knew what we wanted to do. We actually had to implement these things. So to bring forward some of our requirements from modeling methodology in the platform itself, the tests had to be written in Python for Locust. The tests must be modeled based on existing dashboards. The tests should be consistent between runs so that they're fully repeatable. And some other considerations we had was that it would be great to increase the velocity for operators if the test could easily be updated. So what we came up with was to actually generate the tests themselves from Grafana dashboard JSON. And we already had some experience in the team with the Grafana dashboard JSON model, so that lent itself well. This also allowed us to model the tests after the dashboards a little more precisely, and it enables quick adjustment to the tests. So if you needed to tweak something, you could just tweak it and rerun the generator, and we have a bunch of new tests coming out the other side. And the nice thing is that it generates a consistent test suite every time. You don't really have to worry about user error. As long as the input's good, the output should be good as well. So the overview of our implementation of the generator itself, we identified some key dashboards in Grafana, things that were slow, things that were fast, things that had different kinds of panels, things that had lots of template variables, things that had no template variables, etc. I think overall we probably identified close to a dozen or so, and we pulled these via the Grafana REST API, and we actually ended up saving a copy of these in the generator repo, and that was mainly due to the fact that if somebody edited the Grafana dashboard upstream, we didn't want to have our tests change on us. We needed them to remain consistent. So we actually saved this copy, like the copy of all these dashboards, the JSON, into our test repo to kind of codify them. So we wrote this Python script to parse that JSON, and it extracts the template variables and the panel queries, and it performs that variable substitution, and it actually uses this data to template the tests with Jinja, which are just Python test templates written in Jinja 2, and they, in this template, would really define the structure for each test, right? For each dashboard, handle the variable loads, handle the panel loads, and these templates, this Python that was templated, it mainly used the new async Locust client to make all those requests. And from the output of this whole system was a bunch of Locust tests that are all valid Python, and they're ready to run. And we would actually, we ended up generating one test per query window, so 1 day, 3 days, 7 days, and 30 days. And this was really just for us. I mean, the multiple tests, it allowed us to test each query window distinctly, but we could load all the tests at once. So we could rerun a specific query window or something if we wanted to without having to rerun everything. And again, for us, just logistically, this made more sense. So now we were just about ready to go. We need to figure out what kind of data we wanted to get out of these tests and kind of what we wanted to compare on. So it came down to choosing some meaningful indicators. So errors to us are always meaningful. They help track your failures under load. More data is always better than less. So we actually chose to record basically everything that Locust provided in our Google Sheet, but we'd really only compare on error rates, your median, your 90 and 99th percentile. So just to dig in there a little more, error rates, they're not only helpful to understand what's currently failing, but they help you understand the point at which your system starts to fail. So you can actually increase load using your load testing tool until you're either content with the performance under load or things start to fail. The next thing is quantiles. These are extremely useful in the observability world, just that most latency-based SLOs are already expressed as a percentage. So for example, you might have something like 99% of your requests complete within X seconds, and the quantiles chosen, they should be meaningful to that SLO, but they should also be wide enough and varied to kind of help understand the spread or how frequent those slow requests are. So for example, your P50 or your median, I mean, half your requests are basically completing in this time. So if this is really good or acceptable performance, then you're kind of already doing okay. At your 90th percentile, only 10% of the requests are actually slower than this. So is this performance acceptable for the majority of users who are accessing your system? And, the 99th percentile, just 1% of your requests will actually be slower than this. So is this a tolerable edge case? And kind of how does this align to your SLO if your SLO is 99% for that latency? So now we built this thing and we needed to turn it loose. So our first step was to identify the current performance of the system we already had. And this is what it looked like. So 30-day windows, you could see were pretty horrendous, and added load really only exacerbated the issue. And 10 user 30-day windows, as you can see here, there's actually no data for those. They are timing out except for the P50. So clearly things weren't great. And just a note here, the y-axis in all these graphs, this is the time in milliseconds for the entire test suite to run. So iteration 2, we thought, hey, maybe other metrics platforms are faster and Thanos is the problem. It couldn't possibly be us. So this is what happened. We implemented a proof of concept for Amazon Managed Prometheus, which you see here as AMP, and we implemented a proof of concept for PromScale, and we ran those against our current Thanos system. So as you can see here from the error rates slide, that as the user range increased, so did the error rates in general. Most of the solutions saw no or little error rates at the shorter, smaller ranges and virtual users, and PromScale had error rates kind of throughout. And Amazon Managed Prometheus and Thanos tracked very similarly, although the Managed Prometheus solution was slightly ahead. In terms of performance, we found extremely similar trends between the platforms for the most part. As user range increased, performance basically became unacceptable again. So the question really became, why do none of these platforms actually work well for us? So the conclusion we came to was basically that given that AMP, which I believe is Cortex-based, and PromScale and Thanos all degraded pretty severely, approaching 30-day query windows, we came to that conclusion that our data was likely suspect, and that the way we were recording metrics was not lending itself well to the way Prometheus, TSDB, or Thanos or something else worked. And a future investigation would actually confirm this, in that our certain series had major cardinality issues, and it was something to the tune of less than 1% of our metric series by name accounted for almost 50% of the total samples per scrape, basically. But in the meantime, until we got to that investigation, we decided to actually use this testing platform to tune Thanos itself. So this was really iterations 3 and on. We were benchmarking changes to the existing platform. The tuning, we focused on 10 user and 30-day query ranges as this was our worst case. And, if we could make our worst case better, then our best cases only got even better, right? So we decided on a potential bottleneck. We investigated how to solve that via configure resource options and implemented. And this is that tight loop again we talked about. And we went through about 17 iterations of these in totals. And every time we went through an iteration, if any increase to the performance or a decrease in error rate was found, we actually implemented that as the iterations continued. And if you look at the graph here, what you can see is that against our baseline, our tuned Thanos actually performed much better than what we had seen previously. And not only was performance up, we were able to get error rates down from about 21% to 1%. So, summary of the changes for those that are interested. Things that had a positive impact were increasing resources, surprise, surprise, like memory and CPU, specifically for store and query pods. Thanos Store, we actually changed that from being a time-based partitioning scheme to hash-based, which is just a configuration option. And this led to some better query distribution. So the Thanos Store or store instances that were responsible for the most commonly queried ranges didn't always get obliterated. We also increased the Thanos Store gRPC concurrency just so more things could get through the door at once. We moved from an in-cluster memcached to an Elasticache managed memcached instance, and this gave us the kind of benefits of a managed service, but also it gave us access to much larger nodes without having to worry about resource constraints inside Kubernetes and working on nodes where everybody else is also running workloads. So we also tuned Thanos store index cache to increase the timeout, increase async concurrency, and increase the buffer size. But we actually decreased the max number of auto connections just so things would get booted a little more aggressively. We also enabled Thanos Store caching bucket, which actually just speeds up chunk loading. And things that we had tried that really didn't work out for us, we tried to overly shard Thanos Store, and we basically found it had diminishing returns after a certain point. We tried Thanos Store shard replicas, but we really found no benefit running that with Kubernetes in just that, like, if a store shard goes down, Kubernetes replaces that pod pretty quickly. And the way this worked was that when you queried, it would actually query across both replicas at the same time. So there wasn't any real performance gain from this. And also we had tried Thanos Store in memory index caching, but it just put too much memory pressure on our Kubernetes nodes. So wrapping it all up, the TLDR slide is that we identified a lack of visibility into the performance of our systems. We ended up designing and implementing this performance testing framework, and we established baseline performance, and we also evaluated other solutions with that framework. This allowed us to draw, then later prove out some conclusions from our test results, and using that same framework in a tight loop fashion, we were able to successfully tune our Thanos and Prometheus instance. So for more information, I'm going to make the slides, the Locust AIO HTTP client and the Grafana test generator available at the GitHub repo you can see there. And if you want to contact me, or if you have questions or you want to share some opinions, my email's on the screen there. And also you can hit me up at the CNCF or Grafana Slack. And my handle is just Brian Groux. So thank you, everybody, for sitting through the presentation. And now we will move on to Q&A. Thanks so much.
Hey, welcome back, everybody. Brian, thanks for an amazing talk and the wonderful memes. I didn't know what Hootsuite was before your recording, so thanks so much for your doing that for us. Very enjoyable.
No problem.
So, Brian, we've got a couple of questions that have come through in the chat. The first one's a double question. The user behavior was codified as Python in Locust. Yep, go ahead, sorry.
Yeah, no, if you want to finish reading the second half, that's fine.
Sure. And the second half is, do the number of developers affect the number of load test users were implemented?
Right. So yeah, the first half, we did choose several dashboards, and the user behavior of loading those dashboards, or what it would look like coming from Grafana, that was definitely codified into the test we wrote, and it did impact the number of users, right? I mean, we found we had relatively low simultaneous users on Grafana at any one given time, so we decided to max out at about 10 virtual users for Locust. Um, and then I think, yeah, like we were trying to determine, I mean, why the performance was slow and not try to find the breaking point of the system. So, I mean, that's really the reason we didn't ratchet up the number of virtual users too high.
Excellent. Thanks, Brian. And look, team, please do continue to put questions through into the chat, the great AV guys, etc., in the background, and the moderators will post them through to us. So please keep more questions coming. We've got about 15 minutes. We will finish at 12:25 Australian Eastern Standard Time on the East Coast for Sydney. Apologies, I can't work out the rest of the 6 or 7 time zone in Australia on the fly, but hopefully you can. So we've got about 15 minutes left before we go to lunch. The second question is, that's the most common type, there should be, what's the most common type of metrics you have seen people overlook? What that would add value to their polling and graphing?
Yeah, for sure. So I've been racking my brain over this one a bit. But I mean, in terms of general metrics for services or applications, I mean, it's kind of hard to say because everyone's stack is so different, right? But in general, I do find a lot of people, they tend to focus on resources, right? Where's my memory at? Where's my CPU? And I mean, that is very important. But I always like to think of things in terms of user experience, and whether it's a real user out there in the world that's external, or whether it's like another service that's using it, or like for our use case where we were providing Grafana to for our users. And I mean, in a lot of these cases, like latency does come in handy, and as I said in the talk as well, and not just running with an average or maxes, but actually understanding the quantiles and kind of how that aligns to SLO and how many users are being impacted through those quantiles. But I think something that's also generally overlooked is that, like, the impact of downstream or managed services your service may be dependent on, and remembering to take their performance and their status into account, both when you're performing your monitoring or writing dashboards, but also when you're coming up with the SLOs for your service as well. I'm not getting any audio from you, Michael.
Thank you. I fell for the oldest trap in the book. Sorry, the next question is, and apologize for my pronunciations here, Greek was not my strength. What is the benefit of Thanos over Prometheus?
Yeah, for sure. So the reason why Hootsuite went with Thanos is that we had a requirement that we wanted to provide our users with up to a year or so of metrics, and we necessarily didn't want to keep all those metrics live in Prometheus and have a massive TSDB. So the benefit for us was really implementing Thanos as that long-term store. But Thanos, and the other side of it is also the high availability side, right? We run multiple Prometheus or Promethei pairs, and Thanos provides the query across that pair, the HA pair of Prometheus instances, and it will also dedupe the results on the other side through the query mechanism. So it kind of bulks out Prometheus, where maybe vanilla Prometheus falls a bit short in terms of HA or long-term storage. And the long-term storage on Thanos is can be sampled down as well.
Excellent, thank you. Well, that's the last formal question. Please do ask more questions. They did foolishly say that I'm allowed to ad lib, which is always very dangerous. So my ad lib question is, what was the biggest surprise you found when running your first test?
Yeah, so the biggest surprise was just how absolutely horrific the performance on querying some of these series were, and it became pretty obvious when we started running these tests manually to begin with, just testing if stuff worked. it became pretty obvious who the worst offenders were. And like in terms of the series, right? Like not the people, but yeah, but it became pretty obvious who the worst metric series were. So when we did perform subsequent investigations, it kind of gave us the, okay, I kind of know where the bodies are buried. I know where to look.
Excellent. And what was the biggest waste of time? Like you spent all of this time coding something up and it didn't actually show any in performance. And what could you learn from that?
Right. For sure. So, I mean, like, are you asking the biggest waste of time that we've hit, or?
Yeah, you
Right.
thought you would find value
Right.
in a space and you didn't
I
actually
see.
find any value.
Yeah, that's a good question. I mean, in terms of the overall system and the approach with using Locust for performance and load testing, we've found value there. I don't think we've fallen down anywhere. I think the only thing that's maybe fallen slightly short is just now that this has worked so well for us, we've been trying to figure out how to scale it to the rest of the team. And, we're trying to figure out if Locust is that tool to do that going forward. And we're actually not sure. So if you want to talk about perhaps burning time, then yeah, we put a lot of time into this and into Locust. And, we may be starting over with something that's slightly more scalable or that we can roll out to the whole org.
Excellent. Thank you. As an ex-software tester, I never found testing or performance testing was a waste of time, even though the other people on the other side of the quad sometimes wondered what we were doing on our side of the quad. Excellent. And what would be your one key takeaway if someone walked in and say, what should I take away from this talk?
Right. Yeah. Like, I think the best thing we've got out of the system was definitely tuning Thanos, and just how easy it was to make a change, run the make a change and run the performance test, and make a change and run the test again, and then actually see those benefits or detriments, as sometimes happened, as we went along. So, I mean, the one takeaway is just say, yes, performance testing is useful, even in infrastructure, even if it's not an end user facing product. Your users, the developers, at the end of the day will thank you.
Good. Excellent. That line between the developer and the end user is sometimes a little blurred with management and cost of performance testing and continuous integration. So yeah, I'm a great believer in it. And as a manager, I'm encouraging it. So yes, wonderful.
Excellent.
Good. I think that's all the questions we've had come through.
Okay.
We might give people an early mark for lunch if they like. You'll get a few minutes early. But Brian will be heading across to the chat in the Venulus. If you haven't found the channels yet, so this is my second LCA, took me a while to find them. Scroll down on the left, go to Browse Channels, and then you'll find a whole pile of channels to join. And if that's why you missed out on some other things, sorry that you didn't hear about that earlier, but please do join Brian. And Brian, a great thank you. Thank you for taking your time, your evening. Thanks your family and plants as well for the after hours work you're having to do in Canada. And please do stay warm over there.
Great. Thanks so much.
Thanks. Bye, everyone. Enjoy lunch.